All right, guys, we roughly left at this point during the last lecture. We described what differentiability means. Would anybody describe it in a very picturesque sense? You know, you just as if you are watching it through the eyes. Tell me what you are seeing when you are looking at a differentiable curve, please. Stephen Lin, beautiful. That's exactly what a differentiable curve is. You zoom in and you are seeing a line. Here, you see guys, here is a curve. Now imagine you're zooming in this curve, you're zooming in, zooming in, zooming in, and it begins to look like a straight line. Good. And that straight line will have the slope that's defined to be the derivative, right? It looks like this. You see, here is the zooming in, right? If I were to zoom in, the left blue line and the right blue line will eventually be the edges of my screen. That means that whatever is beyond this blue line is beyond my visibility, beyond my horizon. And so any other point, if I'm an insect standing at point P, any other point I'm going to see is going to be a point Q. And between point P and Q, I can draw a straight line. So the set of all possible straight lines, or I call it a bouquet of lines, if the function is differentiable, the lines will start having the same slope. That's what the limit means. You understand? So as I zoom in, what I will see the line whose slope is what we call the derivative. And for my other class in the evening, in office hours, I showed a little bit more, something that you will see later in this geometry. Okay, later in this geometry, I will show you that you can actually, if you understand this geometry, you can figure out many derivatives like this. Okay, if anybody decides to stay after class, I will show that. I will do it also later in the semester, but the earlier you understand it, the better. Okay. And one other thing is I would like you to grasp this idea that if you go to calculus 3, you will see a shift in perspective. The derivative will be no longer the slope of some tangent line, it will be the actual tangent line. Because if you think about it from a geometric point of view, what matters is that you are zooming in on a curve and it looks like a straight line. That's the only thing that matters. Slope is a very arbitrary because you understand that here I decided what's vertical, what's horizontal. I can tilt my axis and change my perspective. And then the slope will be a different value. But the line and the curve, they still stay the same. Now, would anybody tell me, please, what's the situation with continuity? Remember that if a function is differentiable, it is continuous, right? Why is that obviously the case? Remember, what is continuity? Continuity means that the graph of my function is one whole piece. You understand? So a continuous function generates a graph or a curve that is one whole piece. So that means that if you pull along this curve as if it were a string, it will all move together, right? The material is attached. So why is that the situation? Somebody said no hole, right? So very simply, because when you zoom in anywhere on a differentiable curve, you're going to see a straight line segment. Yes, it looks to you like a straight line, and straight lines are continuous objects. And we proved that using, whenever you even have an intuition, you always wonder, how do I prove it, right? So who knows, straight line, is it truly a continuous object, truly a connected object, or maybe I just am erring? You get paranoid. So this is what it means algebraically or formally. We are interested to know what's limit as x goes to a of f of x, but we only know that this limit exists, and we might kind of suppose it has a theoretical value. So we have limit as x goes to a. I'm going to try to construct this limit out of this limit, which I know. So my first step is to have this numerator. So I have f of x minus f of a, and I pay for it by pulling in front f of a. And then all I need to do is multiply and divide this part by x minus a. And I have this expression. So limit of f of x is just the same as this limit here. Yes? Now when I take the limit, this is just a constant, it stays. The limit of this part is the derivative, and the limit of that part is 0. So I just get f of a. Now here is the question, guys. This is already new. Now, if I have a continuous function, does it mean that I also have a differentiable function? In other words, if I zoom in on a curve that is one whole piece, does it mean that it starts looking like straight line segments? In other words, zoom in at a point, it looks to you like a straight line. Zoom in somewhere else, it looks to you like possibly another straight line. Question makes sense? So type in the comments whether you think continuity implies differentiability. Alexa says yes. What about the rest of you guys? Okay, so Steven says possible sharp points. Wonderful, interesting. And okay, so guys, go on. I want to hear your opinions, right? You can see it, right? You're looking at a curve that is somehow one whole piece, continuous curve. You're zooming in at some point. Does it mean you will start seeing a straight line segment? That's the question. So Lakey says yes, but not the other way around. You have to be careful, Lakey, right? What do you mean? You see, we examined previously that if a function is differentiable, that is, what is differentiability? A curve that you zoom in at a point, it looks like a straight line. Anywhere you zoom in, it looks like some straight line. It's really the reason why we thought, or at least many people thought, that the planet is flat. And still there are people that are flat earthers. They would say that, well, the planet is not a sphere of sorts. Why do they think so? Because they are very small compared to the planet, and they are zoomed in at a point, and it looks like a tangent plane. You understand? So if it were a perfect sphere, we are not living in a perfect sphere, then everywhere you would stand, you would imagine that you are standing on a perfectly flat plane. Yes, like differentiability always means continuity. We proved it formally, and we had an intuition about it. But you're saying continuity does not always mean differentiability, which means what? Which means that the curve could be continuous, but you imagine you can zoom in at it and not see a straight line. Good? So you are not answering those questions, most of you, so let me not pull teeth as we need to move on. Indeed, Lakey and Christian and a few people, you are correct. All right, here is a simple example. Imagine that I have this particular line segment, so this particular curve, it does look continuous, correct? Because it looks like one whole piece, it's all connected here. So I zoom in at the peak, and what do I see? I see a broken line. And no matter how much I zoom in, I will always continue to see a broken line, correct? So notice that it's differentiable anywhere to the left of this peak and anywhere to the right of this peak, because zooming in at this point, what will I see? I will see a line, correct? What line will I see? I will see that same line. I zoom in here, I will see, no matter where, I will see that same line if I zoom in here, okay? So that means that it's only not differentiable at the peak. And here is another situation. Notice that, so differentiable functions are pleasant to the touch. That's what you should think of it. They are called smooth curves. Smooth because you understand, everywhere where you pet this curve, there are no sharp edges, nothing like this. So this is pretty sharp. The angle here is sharp, but there are some things that are called cusps. They are worse. Okay, this is a cusp. It's much worse. Now you see why it's worse, because not only do we join at a sharp edge. The sharp edge, look at it. The angle is going to 0. This angle here is going to 0. Can you tell me, please, what do you expect the derivative to approach? Let's say I take it from the right. I take this point. Are you with me, guys? I cannot see most of your faces. That's kind of, you know, I do not know your reaction. You see, I have this point and I hold this point, right? You can connect them with a segment of a line, right? You can connect them with a line. What slope do we have here? Is it positive slope or negative slope? So this is my point P, and I have point Q selected to the right of point P. Your point P is right over A, right? I select this point here. Do we have a negative or positive slope, please? Muhammad says negative. Steven says negative. And you all see that it's negative because what do? You're seeing that if I move to the right, I'm dropping down. So that means the slope is negative. Everybody is clear how I know that without any calculations, right? If I move from A slightly to the right, you always, when you calculate slope, you might as well assume that the run is positive. That means you go to the right, and as you go to the right, you're dropping. So it's negative. Now, when I push Q closer and closer to P, what's going to happen? Do you see what's happening? The line is getting, oh, if this is my line, can you see the camera? It's getting more and more vertical. So it's negative and vertical. So the slope I will get if I go to A plus, it's approaching positive infinity. Sorry, negative infinity, my apologies, right? So that's what you have over here. You see, as x goes to A plus, we're approaching minus infinity. If I do this from the left, you can see that this line now is positive, but I push this point Q from the left, and I approach positive infinity from the left. You understand? So when your slope approaches positive, negative infinity, that's a cusp that's very, very sharp. Here that doesn't happen. Here it will approach positive slope, finite positive slope, negative finite positive slope, right? So this is not as terribly sharp. So this in some sense less differentiable than this thing, yes? But we already see that, in other words, this is sharper. You see why sharper? Because here the blade is at some positive angle, and here the blade is just is sharp, is just reduced to a point, right? The angle is reduced to 0. It's sharpened to 1 point. That's what I wanted to say. And here is the example of this particular type of graph. This is an example of this particular type of graph. And here is that function, 1 minus absolute value of x, okay? So where does this function fail to be differentiable? Some of you naturally will start graphing it, but you see, you are only successful to graph this particular, you would only be successful because this function is simple. You want to try to think with your eyes closed, okay? Where is this function not differentiable and why? Okay, so let's look at it, right? So this is the graph. I drew it for you, but that's not necessary, right? Here is how you can think of without drawing the graph. What is absolute value of x? Absolute value of x is negative x, right? Look at it, we subtract absolute value of x. So absolute value of x is negative x if x is less than 0. So we are dealing with 1 plus x, 1 minus x. Now, if I look to the left of 0, what object is this? 1 plus x is what geometric shape? Write in the comments, talk to me, guys. 1 plus x is what geometric shape? Just 1 plus x alone. Muhammad says a line, and Steven says a line. Yes, this is a line. You agree? So without doing any calculations, tell me if this is a line, what does it mean about, what do we know the derivative to be for all x less than 0? For all x to the, what is it, to the, what is it, is it west? Yes, west of 0, I think, right? So to the negative of 0, what will the derivative be? Please tell me. Look at this thing, what the derivative will be, doing no calculations whatsoever. Yes, Sumaya says that would be 1. Why is that? You understand? If you understood that when I zoom in on the curve, I see a line. And the slope of that line is the tangent line. That was the bouquet of flowers argument, if you understood it. Which means I look at this expression, I look at the slope. Slope is 1 here. It's right next to the x, yes? So I know if I look anywhere to the left of 0, I see slope 1. If I look anywhere to the right of 0, I'm on another piece of line, right? And therefore, the slope here is minus 1. You see, so above 0 it's -1, below 0 it's 1, and at 0 they don't agree, right? It's +1 to -1. It's a broken line. Here you can see it here. Yes, but you notice I drew the picture. I could have done it without any without this drawing. I can just look at the formula and I know the result, right? I can kind of use sonar in a sense to know what this graph is about. Here is this calculation at 0 done formally, right? So I push x to 0 plus. If I push x to 0 plus, that means that I'm located on this line, and of course I will find slope to be -1. Why that way? And you can see, okay, f of x minus f of 0, it's 1 minus x minus 1 over x. When you simplify it, it's minus x over x. Cross out the x's, it's -1. If I approach from the left, of course, I'm on this part and I'm expecting slope to be 1, which it is, because f of x is 1 plus x. And then I subtract f of 0, I subtract 1, divide by x, it's x over x, which is 1. Good? So 0 plus and 0 minus exist, but there is no limit at 0. Good? So this is called, it's left and right differentiable, but not differentiable, because the entire limit and qualified limit does not exist. Am I clear, guys? Right? Yes, if you understand. I'm trying to kind of speed things up. We're very much behind, but I expect it to be so, right? And of course, guys, if you, as I know, as some people admitted it, of course, in the last class, some of you assume if you can solve the problem some other way, just doesn't matter. If you think if you can solve a problem and you didn't have to go through any sort of thinking, then you assume that I'm overcomplicating things. Maybe I am, maybe I'm not. The question is, open that book on physics. If you can solve those problems, then I'm overcomplicating it. If you cannot solve those problems, then I'm not making it complicated enough. You understand? The question is, what is your goal? Most of you have the goal of just, I don't want this class, I imagine. Let me just finish, do the least amount of work possible and get on with my life. I cannot, of course, change that. I hope that, that it will become exciting to you, and that you would see some higher purpose for this, right? So you can come out of college and know nothing at all, because most of your classes are complete nonsense. Maybe even this class is a nonsense, right? And that's not an assumption. I just know. I've taken psychology classes, almost graduated with psychology degree, with philosophy degree, naturally German, and all sorts of other things that I did in college. Okay, and I would say pretty much most of it is complete bullshit. I hope not my class. Okay. So because it goes on, you cannot imagine what incredible things you can consider. As I mentioned, quantum mechanics, it's entirely probability theory and functional analysis. So that's the mathematics of it, right? So you get a sense that you don't get from other things. So yeah. There, if you believe it, such geeks that actually decide to join my class even though they don't have to, right? So from just some people find it. So that is pretty exciting. I hope it would be some of you eventually. So the question next is, what about this, right? So can we have many points of non-differentiability, right? In this previous example, there was only one sharp point. Can we have infinitely many points of non-differentiability? What do you think? Steven says yes, and can you imagine it? It's enough if you can imagine a picture, and it's of course even better if you can come up with some sort of function with a formula. But pictures are pretty good as well. Yes, so only a few people mentioned. What about the rest of you? Sleeping still? Dreaming? I hope you're dreaming colorfully, guys, right? My dreams are very vivid, right? If your dreams are vivid, you have good imagination. This material should not be a problem then. So, can you see it? Tell me, differentiability, sorry, points of non-differentiability. Can I have infinitely many points or not? All right, you don't want to talk to me. What can I do? So here is a simple example of infinitely many points of non-differentiability, right? It's not differentiable anywhere where you have this sharp edge. Germans call it zackig, right? So it's like zigzag, but I really like the word zackig. It really sounds like what it is. Yes? So what sort of function is this? It's an actual function. All you have to do is, for example, f of x is shortest distance from x to an integer. In other words, take the number 1/2. What's the shortest distance of 1/2 to an integer? Well, either the distance from 1/2 to 0 or from 1/2 to 1, and the distance is 1/2. You agree? Take the number 1.3. What's the distance to an integer? It's 0.3. Make sense? So so what is the slope here? What do you think? What is the slope? Can anybody tell me what's that slope? It's very simple. Look at here. The distance here is 1/2, right? It's linearly increasing, right? So let's say from this point, it's like you can imagine that this is 0 because it doesn't matter. You're measuring distance from, let's say, one number to an integer. It says you can just reduce it to measuring the distance from 0 to something between 0 and 1, right? So this distance is what? This here is length 1/2. And how much do I climb for a length 1/2? You see, what's the distance here? So let's say 0.3. 0.1, 0.3, it's 0.3, 0.4, 0.4, right? So it's what's the rise over run? What do you think? Irvin says 1/2. But what about the rest of you? What do you think? Rise over run. What is this length here? What is the length from this point to the middle? The length is 1/2. Right? If I move 1/2 units to the right, how many units do I climb? From this edge, how many units do I climb? Well, think about it. What's the distance of 1/2 to 0? Well, no, I don't climb 2 units. What's the distance of this point? Let's say it's, what is it, 2.5. I don't know, right? What's the distance? Yes, exactly. So the slope is 1. So this point is, this is of length 1/2 as well. I mean, I might have not drawn it perfectly, but this and that are the same length. This is 1/2. You understand why, yes? Because the distance of 1/2, I call it 1/2, of course. You know, somewhere else doesn't matter where it is. I can always assume that the integer is 0 here, right? Make sense what I'm saying, guys? Because maybe this point is what is it, 2.5, right? Then the distance to 2 is 0.5. Understand? So this length is 1/2, and what is the rise? It's you're climbing from 0 to 1/2. Good. So 1/2 over 1/2, the slope is 1. This slope, the downward slope, is minus 1/2, right? So this is, sorry, minus 1, not minus 1/2, right? So this is built out of shapes that are very similar to what we observed here. It's basically many teeth like this. Good. Now notice that in this picture, the sharp points are separated by some smoothness, right? So there is something smooth to the left of a sharp point and to the right of the sharp point. Here is another sharp point. There is smoothness to the left and to the right. Good. In other words, if you zoom in slightly to the left or slightly to the right, ever so slightly, you are going to see a line segment. Now, my final question regarding this type of graph is this always the case, guys? You understand what I'm asking? If a function fails to be differentiable somewhere, will it mean that slightly to the left of that point or to the right of that point, very slightly, it will be differentiable? You understand? So we have this picture that that if we zoom in on a curve, you're going to see line segments. This is not differentiable because you see in between the line segments, there is no other line segment. You see, so differentiable curve, you're zooming in, you're seeing line segments. Zoom in between those two line segments, you're seeing another line segment, right? But here it's like a chain of line segments. So here it's not differentiable. Is this the most general picture for non-differentiable functions that are continuous? Is my question clear? I'm asking basically if I have a non-differentiable point, a non-smooth point, will it mean that if I move to the right or to the left, I will find smoothness nonetheless? So Steven says, yes, I believe so. What about the rest of you guys? So you have that picture that if you move slightly to the left or right of a non-differentiable point, you will see smoothness, right? So you are in good company, but in very old company. In other words, you see, to me, the answer was right away no. And why? Because I worked at the aquarium. Did I tell you that? I used to work at the aquarium. And what do you think was my specialty? Those were horseshoe crabs and sharks. And do you know why? Because everybody wants to work with otters and with all the fluffy, cute animals. I like fluffy, cute animals, but I hate children, right? And they go, they scream around, scream and have those idiotic questions. So I wanted to be left alone, right? So for example, they come to the touch pool, it's freezing colder, and somebody comes, you want to pet this thing? No? Oh, goodbye, right? That's why I was working in the aquarium, and I just enjoyed watching the sea stars move. Like by the time the sea star moves from the right edge of the tank of the aquarium to the left edge of the tank, I could go home, right? So it's like a clock, right? It's a time clock, right? So there I looked at sharks, and of course they have interesting teeth structure, right? Megalodon, have you ever seen a megalodon tooth or pretty much any shark tooth? It roughly looks like this. I exaggerated the zigzag shape on the ridges, but what you're going to see is a tooth, and upon the teeth you will see more teeth, small teeth, right? And upon those you will see further teeth. You understand? A shark is very, very not cute. If you know Bertolt Brecht's song, it was pretty popular. I like it in German. I can play it to you if you want to. In English, there's a translation of it, but the English one is kind of doesn't get me, right? Und der Haifisch, der hat Zähne und die trägt im Gesicht. So which means, oh, the shark babe has such teeth, dear, and it shows them pretty white, pearly white. But that's not exactly that. You know, basically the shark is having those sharp teeth and it's right in your face. It's sharpness upon sharpness upon sharpness. There is no cuteness to a shark, right? At all. My God, right? So here is the function that will be a shark function, right? It would be just teeth upon teeth upon teeth and nothing else, just teeth. Yes? Now, what I'm saying, guys, I mean, I drew a pretty crappy picture of it. I just, it's difficult, right? I got lazy. But you understand what it would look like? It would, this f is my original distance to an integer function. And what I do is I just take the teeth and I superimpose them with more teeth. And upon them, I superimpose with more teeth and onwards. You understand the idea? So it will be teeth upon teeth upon teeth. And you can show formally that there is just not a single point of smoothness. You are going to be cut no matter where you zoom in, right? It's a type of discontinuous curve. Most curves in nature are not discontinuous, sorry. They're just, yes, infinite teeth, exactly, Stephen. Most curves in nature are just everywhere sharp, you understand? There's just no smoothness whatsoever. It's kind of like what life is, right? There is nothing nice about it. There's just sharpness and sharpness and sharpness. No mercy, keine Gnade, as the Germans say, right? No mercy. Okay, here's a comprehension check, guys. Let's see if you are with me. Without doing any computations, find the derivative of 5x plus 2. I think it's plus 2. Yes, plus 2 at x equal to minus 7. So you should see right away what's the derivative. Okay, I want you to tell me what's the derivative at minus 7 of 5x plus 2, please. Go ahead. Write in the comments. You should kind of see it like this. Okay, I will wait before I reply. I want more people to participate. Kirill, Dana, right? Come on. I want you to see it. you are basically training your it's like learning to walk, truly, right? My little giraffes, beautiful. You're beginning to walk, right? All we need is just another, what, a year or two, or maybe 5 with you. You will be PhD students. Good. Beautiful. Beautiful. It's 5. Now, would anybody like to explain to me why can you see the answer is 5? Very simply. It's already aligned. Amazing, right? It's already aligned. You are zooming in on this curve, and this curve, if differentiable, will start looking like a line. Obviously, a line will continue to look like a line. Yes? I'm presuming, when I say obvious, I sometimes get paranoid. Is it obvious? Because, guys, you know how many times mathematics is going to scare you, disappoint you, or just completely turn your ideas upside down, right? So you become very paranoid. Sometimes the paranoia, doesn't pay. In other words, well, you get obvious results, but also very frequently you have an entirely surprising result. Okay? To be weird, of course, if you zoom in on the line, for it to change and become not a line. Okay, so yeah, this is what happens. Zoom in on a line, it looks like the same line. And when we ask for the derivative in our class, it means we're asking for the slope of that line, which is a bit arbitrary. To differential geometry, the only significant feature, and that's what I'm again saying here, is that you zoom in on a curve and it looks like a straight line. Okay, now slope is arbitrary because of the following. You see, I try to explain to you this. Okay, here is a coordinate system, right? This is xy coordinate system, and there is a green xy coordinate system, right? And then I look at this line. You see, there is this line here. Now, in the xy coordinate system, it looks like y equal to 1 times x plus 0. Now, relative to the green xy coordinate system, it looks, look at it, the green x-axis is parallel to the line here. So it looks like it has slope 0. Relative to the green coordinate system, it looks like it has slope 0 and intercept maybe 1, you see, because it goes through this point here, okay? So it looks like y equals 1. So all lines, every equation of a line that you come up with, you're really describing the same line, essentially. It could be vertical line, and you said it has no slope. That's only because you're using coordinate systems where it doesn't have a slope. You understand? So there's only one line to a differential geometry. And this is a very useful idea, which I trained, I think, about 8 people already in my other class in office hours. That will be important when we talk about implicit differentiation, okay? So this is the picture over here, right? So this curve is root of x. And if you view it from the green perspective, it would look like x squared, okay? And basically, to a differential geometer, the graph y equals root of x and the graph y equals x squared are the same picture. You understand? It's just a different perspective. Are you following me, guys, what I'm saying? So you have fewer functions, far fewer functions if you are a differential geometer. Root function and square function are the same thing, truly, because they have the same graph. They have the same shape of the graph. And therefore, when I find derivatives to roots, I do it at the same time to squares and vice versa. Okay, so this is a bit hard to read. And this is only a flavoring, okay? So what's the derivative of y equals x squared? Maybe I can draw it for you to give you a flavor, okay? So, okay, let's see. So new share, whiteboard. Okay, guys, are you ready? So suppose that, yes, Alexa, it's 2x, beautiful, right? So we are going to do it very formally in a moment, I hope. But I just want to show you the idea, the perspective of differential geometry. And if you think that this perspective is, you find it needless, that's only because you haven't encountered more interesting problems. The entire theory of relativity is a matter of communicating perspective. You understand? And communicating your perspective to another person that looks at the same thing but from a different perspective is very difficult. Okay. So here is a curve. here is that curve, guys. This is the curve y equals x squared. Now, what is the curve y equals x squared? That's just a shorthand for saying that the first coordinate is just some number, and second coordinate is that number squared. Yes? Make sense? So this is x, this is here y. Good? I will actually try to talk about it keeping the same coordinate system. Okay? So then let's suppose that we have two astronauts that are making a spacewalk. So there is the astronaut walking on the x-axis, right? And there is, so he's watching, he's looking at this point over here. And he's seeing that there is a tangent line. Yes, guys? This astronaut is staring up, and he is seeing a tangent line here. Now, there is another astronaut who is doing a spacewalk on the y-axis. So the y-axis is horizontal for that astronaut, and he is looking up. Are you with me, guys? So tell me, this astronaut, what curve is he seeing? What's the formula that he's seeing? If the first astronaut is seeing x squared, what is this astronaut seeing? You understand what I'm asking, guys? This is x squared. So basically this is saying, well, the point at which I'm standing, the altitude. So if my horizontal, my latitude, or whatever we call it, is x, my altitude is x squared, right? If the altitude for this point, right? Because the second coordinate, no, Steven, not y squared, because they're watching the same curve, right? So he's in position y, and that means he's looking at the second coordinate, right? So he is looking at the second coordinate, and what he's seeing. Yes, do you understand what's happening here? What is x squared, guys? Don't think of x or y. That's very confusing. This just means that this is the type of curve where the altitude is the square of the horizontal position. So if that's the case, well, for him, the horizontal position is the altitude of the second guy, which means that what he is seeing is, well, he is seeing I'll keep it in the same coordinates. He's seeing y, but what is what's the first coordinate that he's seeing? Well, he's seeing root of y. It's almost like passive, right? So what is it? If the second coordinate is the square of the first coordinate, that means that the first coordinate is the square root of the second coordinate. Do you understand? It's just a change in perspective. What is this? This is saying second coordinate is the square of first coordinate, and this guy, let's say that they agree that we're going to keep y the second coordinate, but for him it's a horizontal. So he's saying the first coordinate is the square root of where I stand. So he is seeing this curve that he is seeing, because this is his horizontal. He is seeing the curve x equal to root y. Okay, does it make sense? So how do they report the slope? So they report the slope, look at it, like this, right? So this is now Leibniz notation. So this is dx, and this is dy, right? So this first guy, is seeing dy over dx. If this is position x, is seeing that this is 2x. We can just clearly do that by formulas, right? He's seeing it 2x. What is this? What is the slope of the second guy? What is his slope that he's seeing in terms of x? Can you tell me right away? What slope is this guy seeing? So, and I see slope. What's the slope that he is seeing of the same tangent line? Look at it. what's the slope? The slope is vertical over horizontal, right? So this one, it's 2x is saying vertical. For this guy, vertical is this line and horizontal is this line. For this guy, is the other way around. Are you following? For this guy, dy is the horizontal. So he is seeing the slope. Horizontal is dy and vertical is dx. In other words, he is seeing 1 over dy dx. Well, 1 over 2x, Stephen. Good? So he's saying 1 over 2x. If we communicate the slope in terms of the same variable x. Are you following? You understand, guys? Because why? Because what is the 1 here? It's because they have an inverted perspective of what's vertical, what's horizontal. Clear? You have poker faces, at least the faces that I can possibly see. Most faces I don't see. It's black squares. Yep. You understand what I'm saying, guys? It's why is the 1? It's because of this 1 over dy dx. He's seeing everything inverted. And then what is x? X is root y. If I want to communicate it, if he wants to communicate it in terms of his in terms of his horizontal position, you understand what you do with the derivative as a function. You mention your horizontal position and the corresponding slope for that horizontal position. For this green astronaut on the y-axis, his horizontal position is y. So then this thing is simply 1 over 2 root y. You understand? I now found the derivative for the radical. It's 1 over 2y. Do you see the relationship? They are the same thing essentially. Yes? That's going to be important later on when we talk about logarithmic functions and whatnot. The quicker you get it, the better. Make sense, guys, what I did? It's just it's very simple. I think from a differential geometry point of view, I see, okay, great. We have we have the same curve. Root of y and x squared are the same curve. And this is just just different labeling. So then I know, for example, that dx of root x, it's 1 over 2 root x. It's just in terms of symbols, because d dy of root y is 1 over 2 root y. It's just the symbol doesn't matter. Yes. Okay, so that's what I described here. Good. Now quickly do this, guys. Could you please draw? I'm gonna wait a little bit and I'm gonna describe this drawing. Here is a curve, and I want you to draw the derivative of this curve. You see, y equals f prime x. What would that look like? Does it make sense? So that means that what are we drawing? We're drawing all slopes. So if I zoom in here, what slope do I have? If I zoom in, what slope do I have? If I zoom in here, what slope do I have? And onwards, right? And then it goes like this. So what will the drawing look like? So you see, so you have a bunch of slopes. It's kind of difficult for you without sharing screen to show the picture, but I will go over it, right? So you can possibly say first line slope, second line slope, you know, because it's made of pieces, right? Third line, guys, careful. Third line is this thing. What is the slope, positive or negative? You can always do this. You can take a straight edge and place it on your curve. If it's a, you can make the tip of the pen be always pointing to the right of your x-axis, and you just place it on the graph like this, and then like this, right? And then you just try to measure the slope of that edge. Yes, Ying, and then so here is the picture, guys. Okay. Here is my picture of the slope, right? So first of all, anywhere I zoom in to the anywhere I zoom in between 0 and 3, I see the same line, and therefore I see the same slope. Do you agree? Are you with me, guys? Anywhere in here I see the same slope. And what is that slope? That slope can be easily calculated. It's what? I take this point, and that point. You see, I need 2 points to calculate the slope. Take this point and take that point. So it's 0, 0 and 3, 3, which means it's 3 minus 0 divided by 3 minus 0, which means this slope is 1. Everybody understands how I got this one? Just whenever you see a line segment, take 1 point on this line and another, whichever is convenient. So this is clearly slope 1. Now between 3 and 6, I have those 2 points, 0.33 and 0.63. Because altitude did not change, it's 0 over 6 minus 3, which means that slope is 0. Yes? So the slope here is 0. At 3, it's not differentiable. You can see because if I zoom in at this point, at 3,3, I am not getting a straight line. I'm just getting a broken line. It never looks to me like it's one straight line. Now, finally, this line segment, it's at 0.63, and the other point is 9,0. So what I do is I take 0 minus 3. That's the altitude 0 minus altitude 3 divided by horizontal displacement 9 minus horizontal displacement 6. Good. And the slope is minus 1. And then here it continues. The slope here is 0 again. Is it clear? So whenever a graph is made of line segments, it's very easy to graph the slopes. Where the line segments connect is where the slope doesn't exist. Good? So if you understood my explanation, guys, write yes, and then we can move on. You can do this particular procedure with any line segments. There are some exams on my website. There will be, of course, another exam, but I definitely want you to go through the previous exams, solve them, so that once we cover enough material, definitely do that and maybe do it on time. Do it, let's say, within 2 hours. That indicates how well you understand the material. Good. So in general, guys, you can figure out the graph of a smooth curve. So imagine that I have this this black curve. It's a smooth curve. I can imagine that it's just a chain of tiny line segments. You understand? So how do I estimate the slope? I imagine it's a chain of line segments. And then I put it in green. Then I can draw the slopes of those line segments. So for example, what is the slope somewhere in here? I just look at this line segment, and roughly by the eye, I see, okay, it's positive slope. Do you agree? Because if I move from this point to the right, I'm climbing. If you're walking to the right, in other words, in the right sense of the x-axis, you're climbing here, right? So what happens here? You're climbing. So first you're climbing very steeply, then your climb is less and less steep. So you see the slope is dropping. You understand why it's dropping? And then somewhere over here, it's flat. That's where you get to 0. You don't pay attention to where the graph is on the xy axis. Doesn't matter, it's negative. Don't get yourself confused. When you draw the derivative, you are drawing slopes. You follow me, guys? So all I pay attention to is whether I go up when I move to the right, or if I go down if I move to the right, and how steeply. So for here at this point, although I'm below the x-axis, when I move to the right, I move up. So my slope is, and I move up very steeply. So my slope is very large. So this dot is somewhat the slope for this entire line segment, let's say, right? And then the next line segment, well, the slope is slightly less steep. And the next, it's less steep until when I reach somewhere around this point, my slope becomes 0. Here locally, it looks like a horizontal line. You visualize it, guys? Yes? Wonderful, because we do want to move to more exciting things. And so then the slope becomes negative. So that's why it drops, this green line drops below the x-axis, negative, a bit more negative. And here it begins to, somewhere in here, it levels up to 0. Somewhere here, it's again 0. And then the slope again becomes positive, reaching its positive peak somewhere in here. And then it starts dropping, quickly dropping up to this point. It will drop to 0 because here the slope is 0. Right, so it reaches somewhere here, it reaches its maximum steepness, then steepness gets down, and then here it's 0, and then afterwards the slope is negative, very negative first, and then less and less negative. So that gives you a sketch of the graph. So if it's a complicated graph, you can just imagine it's made of many tiny line segments. In essence, the idea is not more different than with this. It's just resolution is here very low, and here the resolution has to be much higher. It's like a polygon made of more line segments that are shorter. Everybody clear on the explanation? So in my previous exams, I'm not sure if I'll do it this exam, we'll see, right? In my previous exams, you can check, there were questions like, here is the graph of a function, draw the graph of the derivative. And the idea of the entire thing is, of course, to train you to think about the derivative, what it means, right? It's the slope in our context. And I hope if you understood the geometric, the differential geometric context, that the slope is not the important thing. The line is the important thing. Good? So that concludes this long lecture, and we begin another one. Derivatives of polynomials and exponential functions. So first of all, polynomials. I'll show you quite interesting things, guys, if you are willing to see those interesting things. So polynomial is just a function that operates using addition and multiplication. Good? So here is an example of a function that operates only using addition and multiplication. You see, I do all sorts of additions, all sorts of multiplications. When you see subtraction, you imagine addition by a negative number. You are adding a negative number, okay? So we have this function here. And then what, right? And then I can rearrange it and make it pretty. I can present my polynomial in terms of the number of times the input x was used. How many times did I multiply by the input x? So when I simplify it and group things, I see -2 times x to the 0. X was not used here. Plus 4 times x to the 1 plus 1 times x squared plus 1 times x cubed. You see, so a polynomial can be presented in this form. That means that in general, a polynomial can be reduced to the form a0 plus a1x plus a2x squared plus etc. anxn. That's a particular bookkeeping. Do you understand what it is, guys? So the important thing is that you used addition and multiplication, and this is a particularly nice presentation of a polynomial where you group the piles based on how many times you multiplied by x. Clear? Every polynomial can be reduced to that. So by the way, let me just ask you this question. If I have the function f of x equal to 7, is this a polynomial? Wonderful. So a bunch of people say yes. Why is it a polynomial? Very simply because it has that polynomial form, but even better because if you don't use some operations, that means that you can express the function in terms of addition and multiplication. You just didn't bother using them, okay? A polynomial is any function that can be described only using addition and multiplication. And of course, not using them, it's fine. You can only use addition, you can only use multiplication, it's up to you. but you cannot use anything beyond it. Good. And then you increase the number of operations, so then you have division, that makes it a rational function. And then you allow radicals, that makes it an algebraic function. And up to this point, we have not considered anything more general than an algebraic function. Good? So that's why some limits are so simple. Usually they are not. So what is the derivative of the function f of x equal to c? In other words, it's a constant function. What's the derivative of that? Muhammad says 0. Now, why is it 0, guys? Without any calculations, how do you know this is 0? What do you mean? Is f of x equal to c is not a line? Irvin, you have to kind of correct it. No slope, guys. Oh, guys, when you say 0 is not slope, that's incorrect. 0 is very much a slope. Not slope is something entirely different. Not slope means that there is no rise over run. 0 is it's like, you understand, guys? Not having velocity is very scary. Having velocity 0 means that you're resting and you're standing in one place. Not having velocity, it's something entirely different. You're associating 0 with nothing. That's incorrect. You with me, guys? So why is it 0? It's because f of x equal to c is what? It's a, well, a flat line, so a horizontal line, better said, right? Yes, Christian, right? A horizontal line. And the derivative is 0 because of that. Exactly, a line parallel to the x-axis, exactly. Beautiful. Now, let's have another example. F of x equal to x. What's the derivative of f of x equal to x? Wonderful. You can see you don't need to do anything because you are watching a line and the derivative is asking for a local slope of this line, but the local slope is the global slope. It's just 1. Good. And then we can, of course, carry out this definition, z equals x, and we have z minus x over z minus x. It reduces to 1. Good. Now, the next question is for x squared. This no longer is so simple. I cannot geometrically just look at it and say, oh, I know right away what's the slope, right? Because it's changing. X squared is no longer a line. Good. And I know it changes. How? Because when I take the derivative, I do this definition. I see that my calculation, well, here it is, right? Derivative is z squared minus x squared over z minus x. I cross out the z minus x. I have limit as z goes to x of z plus x, and that's just 2x. Because the slope depends on x, it cannot be a line. Do you agree? At different x's, that means we have a different slope. Are you with me? Different x's, different slope. It's not a line, obviously. Now your next task, guys, can you calculate the derivative of x cubed? We're learning shortcuts now, okay? That's the beginning where we learn shortcuts. But for that, we need to do those long calculations. What's the derivative of x cubed? We know the derivative of constant, of x squared, but what about x cubed? And I don't care if you remember the formula, naturally, right? So some people write a formula, but unless you, I mean, I didn't ask you to provide all your work. We will do that, but I want you to guys to, before you use any shortcuts, if you know such shortcuts, to understand why the shortcut works. Good? So let me know when you're ready to discuss x cubed and what it involves to find the derivative of x cubed. All right. So some of you did it already. So let's Let's look at it. So first of all, guys, to carry out, if I use notation 1, as I call it, then I have to calculate limit as z goes to x of z cubed minus x cubed over z minus x. Yes? And for that, I need to cancel out z minus x. I need to factor difference of cubes. How do I do that? Let's say I don't remember that, we can use long division. I just take z cubed minus x cubed, then I divide by z minus x. And I hope you know how to carry out long division. We can talk about it if not. So first of all, I think, what do I need to multiply this expression by to get a z cubed? Clearly, I need to multiply by z squared. So then I put z squared here, I multiply it through, and I get z cubed minus x z squared. I subtract from this line that line, and I obtain minus minus, it will be x z squared minus x cubed. That's my new line. Now, what do I need to multiply z minus x to get this line? Clearly by x times z. So I multiply by x times z. I put it here. X times z times this expression is this line. I subtract. I get this expression. So what do I need to multiply z minus x to get this leading term? Clearly by x squared. Yes. And subtracting, we get 0. So that, what does it mean? It means that to factor out z cubed minus x cubed, all I have to do is I have to write z minus x times z to 1 power less, look at it, z squared plus x to the power of 1, z to the power of 1. Notice, you see, we had z, it had power 2. Yes? Now z has power 1. Now z has power 0. Yes? And then I can cancel it, and then I push the limit as z goes to x, z squared plus x plus xz plus x squared. Each of these terms, they become x squared. So we have 3x squared. So that's why this is 3x squared. We're going to try to figure out what is this pattern, and then we don't have to do the definition. Then we have the shortcut. That's, if you took calculus before, that's a quick way of doing it. But it's quick only because you realized what the long procedure will accomplish. Good? Now here is the next problem. Now you find the derivative of x to the power of 4. In some sense, it can be done easier, but let's see if you can figure out. Well, let's see what you say. X to the 4 now. Notice we know the derivative of x cubed is 3x squared. What about the derivative of x to the 4? Yes. Yes, okay, a bunch of you know it, but I hope that means that you know it because you actually carry out the calculation and not by some memory. Yes, okay. Now, you can do it simpler than what I present, but let's try to carry out the factorization. Are you there, guys? So if I don't see the pattern, I can always use long division. Good? So it's z to the 4 minus x to the 4 divided by z minus x. What do I need to multiply z minus x by to get z to the 4? Well, clearly z cubed. So I multiply by z cubed. And you understand how long division works, guys, right? If not, we can talk about it after class. So you have this calculation, and the result is that z to the 4 minus x to the 4 can be factored as follows. It's z minus x. We have z to 1 power less than 4, it's z cubed, plus x to the power of z squared plus x squared times z plus x cubed. You with me, guys? Everybody understands this pattern? It's, you see, it's z to 1 power less than 4, so it's 3, and then z will give its powers 1 by 1 to x. Look at it. The powers over x and z combined are always 3. So here z gave 1 power to x, here gave the next power to x, and here z gave its final strength to its final power to x. And then when I push the limit, I just have x cubed, x cubed, x cubed, x cubed. I have 4 copies of x cubed, which is 4x cubed. Are you seeing the pattern? How would you factor z to the n minus x to the n in general? What you don't have to write all of it, but you can write dot dot dot. How would I factor z to the n minus x to the n? What do you think? Well, but what would the factored form look like? You dividing it in general, you can notice, you can already notice the pattern perhaps in the previous examples, perhaps, right? If not, think about it, right? What was it with 4? It was, look at it, the power of z is reduced 1 by 1, and it gives all its powers until z is gone to x. And that was the situation in z cubed minus x cubed. We have just z raised to a power 1 less than this, and it gives all its powers, z gives all its powers to x. So that gives you a hint on what's the factorization of z to the n minus x to the n. Yes, Hu Wang, you are correct. So let's do it, guys, together. And its pattern is very, very easy to remember. It's a very tragic pattern. So here it is. It's z minus x, and then z has 1 power less than n. And then z will give its powers 1 by 1 to x. You understand? And that is why I made you, because you see, this is what I mean by reading a sentence. It's very often, that's what you do in combinatorial arguments, is when you read a formula, you realize it's a code for a story, okay? So you can read it and it's a story. And when I look at it, I right away see Oscar Wilde's short story, The Rose and the Nightingale, if you watched it, right? Z is the nightingale and X is the rose. And this nightingale is singing and bleeding to make this rose blossom and become red. So here is the power of the nightingale. It gives its power 1 by 1, one integer at a time, until it is entirely gone, until there is no z, until the nightingale is dead. Yes? And of course, in this question, notice that the rose, the nightingale did it for a student. So who do you think is that nightingale? It is me. Yeah. I'm bleeding, right? Or bleeding and losing my freaking mind and becoming dumb because I have to repeat all this nonsense, right? Again and again and again. And you, what do you care? You will throw this rose away. So I hope you did watch this. Yes? I was hearing myself. I thought somebody intelligent was going to talk, and okay, I realized it's just me. My echo. Okay, guys. So I did. I see the one reason I didn't send you the story in writing. I figured when you're hearing it, maybe you will listen to it. Maybe it will be, you think 13 minutes and you will listen to it, then you will do it, right? But I'm not even sure that of that. So the reason it's interesting to me, one reason, guys, why mathematics is interesting to me is that you can see that many formulas are actually codes for something happening. So let's say, I mentioned it many times. I would sit in a train, and I remember hearing two girls discussing their shoes, discussing what shoes they're wearing, and it's very boring to me. But then I look at some formula some sort of a mathematical equality expression, and suddenly I realize, oh, it's really just the two girls talking about shoes. And when you make those associations, you realize that you can solve this formula by understanding which shoes the girls prefer, or by so you do one of two things, right? Either the formula can be solved because you know what shoes the girls prefer. I can show you many examples of that. That's especially true in probability. Or if you can solve this formula, then you will know what shoes those two girls will prefer to buy, right? And somehow the formula solving it by itself is not interesting. The shoes are not interesting, but in combination, it's extremely interesting. All right, so here is an example of how that works. Z to the 6 minus x to the 6, for example, can be written as z minus x, z to the power 5, plus x times z to the 4, plus x squared, z cubed. You see, z is losing the power 1 integer at a time, and that integer is moved over x. Good? So once you realize what this pattern is, you can realize it by playing with long division. Once you say, well, here is the pattern, you can easily prove that the pattern holds. Because if s is this summation up to n, I can multiply s by z, and I get this value. I multiply s by x, I get this value. When I subtract zs minus xs, I can factor out the s, it's z minus xs, and that will be z to the n minus x to the n. Only this thing survives and only this thing survives. So that proves that the pattern is as we expected. And here is our theorem. The derivative of x to the n, it's called the power rule, is just drop the integer in front and subtract the power. So you see, once you have this theorem, you don't need to carry out this annoying calculation again and again and again. Yes? So the derivative is, I can just do it once for generic positive integer n. So I do it for x to the n, z to the n minus x to the n. I factor it out. I have this factored form. I can cross out the z minus x. And then I take the limit. Now let's look at how many terms am I going to get. So z to the n minus 1. This will become x to the n minus 1. This next term will also be x to the n minus 1. Do you agree? Because the sum of the powers of x and z is always n minus 1. But z is morphing into x. Do you understand that I'm adding the same term again and again? I'm adding the x to the n minus 1 term again and again to itself. And then the only question is how many total number times do I add? How many total number of times do I add the same number? So I see that I have 0x, here I have 1x, 2x, I have all the way from 0 to n minus 1 x's here, right? So I have a total of n summands. You understand? N summands. So that's why it's the same number. It's n times x to the n minus 1. Did you follow my explanation, guys? I went fast. I hope that means you understand why that formula works. Okay, so that's for polynomials. So here is what it just means to us, right? Here is a very easy example. What's the derivative of x to the 6? Now, once I realize this pattern, I don't need to do the calculation all the time. I did it here with the n. I did it for all possible positive integers n. Do you understand? So I solved this problem already once, so I don't need to solve it again. The derivative of x to the 6 is 6x to the 6 minus 1, 6x to the power of 5. The derivative of x to the 101, it's 101 x to the 100. Yes, of course, Alexa, you can find the derivative of the derivative. That's a new function, and you can find derivative of the derivative and do it again and again and again. And not only can you, it's a very useful thing for many applications, as I will show you as we progress to exponential functions. I can show you pretty amazing things, guys, but the more amazing they also become very difficult. You understand? Amazing things tend to also be difficult, and what's difficult is not pleasant. It's also what happens with music, right? Why do you like pop music? Because your brain is resting. You listen to pop music, your brain is not doing any work, and the brain likes to rest. Right? So that's and if it's so that it's there was a mathematician. He defined, I think his name was Birkhoff. It was American. He defined what beauty is. Beauty is the amount of information divided by the difficulty to obtain this information. So the more difficult it is, the harder it is for you to perceive it as beautiful. So the derivative of x to the 6 is 6x to the 5. Of x to the 101, it's 101 x to the 100. Derivative of x to the 30 is 30x to the 29. Do you understand, guys? We now are able to use the shortcut, but I implore you, understand why a shortcut works, guys, right? I obviously don't teach you this class to do something the stupid, difficult way. I want you to realize two things. That the problems, real problems, when they arise, they are not going to be find the derivative of some function. Usually, if you're already at that stage, you already solved the problem. It is the setup of the problem that's most important. And the setup usually will be in the definition of the derivative. You just find out something, you have a formula that looks like the definition of the derivative, which you can afterwards convert to shortcuts. So now we are going to progress and figure out how to do derivatives of polynomials. And for that, we need the following two theorems. Okay, so if f and g are differentiable functions, and c is a constant, we want to figure out what's the derivative of constant times the function, what's the derivative of the sum of two functions, and what's the derivative of the difference of two functions. Really, 2 and 3 are the same problem. Good. Or if I know 2 and I know 1, then I right away know 3. So let's do that quickly, guys, as we need to move. So by definition, the derivative of c times f of x is, and by the way, I can show you how to do it using geometry as well, right? Using zoom in idea. So this is just by definition, the derivative of c times f of x is the function, this is my function, evaluated at z minus the function evaluated at x divided by z minus x. And I take limit as z goes to x. Now I can factor out the constant. And so clearly the derivative of a constant times the function is constant times the derivative of the function. The derivative can move through the constant. And notice it's not the same thing. Some people might have said it's 0 because you see the derivative of a constant is 0. But why is that the case? Constant by itself is just a horizontal line. Constant times another function is not necessarily a horizontal line, because the function might not be horizontal. So for example, 5 times x. 5 times x, it's constant times x, but the curve is not a horizontal line. So the derivative will not be 0. Make sense? Always think about it, guys. If you don't think, there can be infinitely many questions, and there will be infinitely many cases. Similarly, what do you think is going to be the derivative of a sum of two functions, guys? The derivative of f plus g, well, what would it be in terms of derivative of f and the derivative of g? Any ideas? Yeah, sum of derivatives. One moment, guys. Give me a small second. Apologies. So yes, let's continue. So the sum of two functions, the derivative of a sum of two functions is the derivative of first plus the derivative of second function, as one person said. Now, why is that the case? You can see that by the, yes, you can say that by the definition of the derivative. If you stay after class, I will show you the geometric point of view, which is especially useful when with multiplication and quotient, okay? So there's, I want to really show you so many perspectives so that you can right away know that, okay? The derivative of the sum is the sum of the derivatives. Always wonder, why is it true visually? And why it's true formally. You want to have the two perspectives. So when I set up the definition, it's f of z plus, f of z plus g of z. It's this function at z minus this is one function at x divided by z minus x. And then I have to know what is it I'm searching. I'm assuming f is differentiable, so that means I can recognize f of z minus f of x over z minus x. And I can recognize g of z minus g of x over z minus x. So I separate, group together f's and group together g's and distribute the z minus x. And I have a sum of two limits. This limit is by hypothesis, it exists, and it's f prime. And this limit is g prime. You understand what I'm talking about, guys? So you have to develop an abstract recognition. Some people do not understand abstractness, right? Although you do, because you understand it in the worst possible ways. You are very susceptible to propaganda. Like people watch, and they are watching a particular event in the news, and that's pretty scary to me. And what they do, they extrapolate enormously. They see something much more general, right? And it's even difficult to talk about it. So you see you have to have this core in you, right? So you make an observation. Can you see what is the observation that you made without any implications that you are adding? The best propaganda, and you can see that when you speak a few languages and you see different news, the best propaganda never tells you anything wrong. Just like a magic trick never shows you anything that's not there. It is just pushing your attention unduly on some particular aspect. And then you extrapolate and reach the wrong conclusion. And in my opinion, part of it has to do with your just with people's this overgeneralization in some sense, and yet an inability to see what is objectively indeed there, right? So when you look at me, what do you truly see? You might see that I'm wearing a shirt, you might, or at least something that looks like a shirt. Truly what you see is only, maybe I'm not wearing a shirt. You see, guys? Maybe. That's my silly example. You see, maybe below this line, you see here is where you see below this line, there are no pens, and maybe whatever is below, you don't know it, right? At all, right? So you cannot assume that it continues to be green. I should actually show you some shirt like this, right? Maybe what you will see is an entirely different part. Maybe I'm a unicorn below this this line. You're assuming I have legs like you have. You're making many assumptions when you're staring into my video, but what you truly see is only what's in the camera. Are you still alive, guys? Do I have legs? It's a very good question, guys. But the point is that you cannot assume that. You haven't seen my legs, and that's a generalization, right? It's, you see, you might say, well, it's silly. Of course I have legs, but you have to know this thing, guys, that the assumption that you're making an assumption that I have legs. Good. That's, you have to be aware of things like that, because it's very, I can tell you, right? It's really funny. Especially I can see what Russian news are like and what American news are like, and I can see comparison in how they present information. And it's very, very interesting is that you can present the same information and just make the person, everything that anybody is saying is correct, but the person will reach an incorrect conclusion because you generalize. And then I wonder, why do you not see that when I talk about abstract functions, right? So this limit is f prime, this limit is g prime. Always know what you're searching for. And of course, property 3 is established by the same way. So here is how that allows us to take derivatives of polynomials. Okay, guys? We will see in a moment your ability to recognize things. Now, first of all, what's the derivative of 5x cubed? This is a constant times a function I know how to differentiate. So that means I can write it as 5 times the derivative of x cubed, which is 3x squared. That's by property 1. Good, guys? And so the derivative is simply 15x squared. Now, suppose I want to take the derivative of this polynomial. There is a lot of additions, subtractions, and multiplications by constant. So I can just say derivative of 3, that's 0. Derivative of 5 times x, you just need to take the derivative of x and multiply by 5. The derivative of 8x, I just need to take the derivative of x cubed and multiply by 8. The derivative of 10x to the 4th is 10 times the derivative of x to the 4th. With me, guys? Do you understand how I calculated it? So now I know how to calculate derivatives of polynomials without doing the definition of the derivative, because I already paid for it with my theories. So go ahead. Here is your function. Please give me very quick calculation of what it is. On the exam, guys, here is this thing. On the exam, follow my instructions. Don't do more or less than what you have to. You understand? If I say calculate the derivative, it means you can calculate it in any way you like. The only thing, of course, the implicit thing that I'm not mentioning, it should be your calculation. Obviously, you can say, well, a computer will do it very fast. That's fair. I mean, truly, if I say just calculate, a computer calculated it. But I want it to be inside of your brain. Type it up when you're ready. That's very good, Alexa. Yes. You don't once something is zero, you don't even have to write it. Right? Zero, you can kind of ignore it. Don't need to mention it. Okay, great. Right. So it's a simple question. Let's move on. Yes, guys. Got it. Beautiful. It's not a mistake to write zero, right? So the derivative is simply minus 2x plus 27x squared. And you recognize what I used here. I used addition laws of differentiation and multiplication laws of differentiation. Okay. Let's now guys, we are going to test. We're going to test your understanding. Derivatives. Okay, here's the question, guys. It's what? It's 3 times 7 is 21, right? So it's all fine. Derivative of 7x cubed is 21x squared. Here is this question, guys, right? I ask you to calculate the derivative of 2 to the power of x. Good. I want to hear what you would say about it. I just want to see. Derivative of 2 to the power of x. I'm waiting in the comments what you would say. Dragon, wonderful, right? 2 times x, x to the minus 1, interesting. Go on, and let's hear from more of you. Okay, interesting, Kirill. Again, we'll see, guys. You will see my point, I hope, once we are there. But go ahead, think about it. I will be back in a minute. Okay, you spend this time thinking about it. Muhammad 2 x times the power of x minus 1. Interesting, interesting. So, guys, why am I not hearing from more of you? Is it for a good reason or for a bad reason? From Christian, from all sorts of people I haven't heard, from Ying Yang, from Anthony Guerrero, Zakia, from Lakey, for whom I haven't heard from. Well, so don't guys worry if you get or not. I'm just wondering, maybe I don't want to add anything before. I just want to see what are you. So Lakey, okay, x 2 to the power of x minus 1. Beautiful, isn't it interesting, right? What about the rest of you? Isn't it obvious, the answer? Come on, I want to see how you are thinking. Well, let's see. So we have Lakey is saying, well, we drop the x and we have 2 to the power of x minus 1. What about the rest of you, right? What do you say? Jonathan Jadu, what about you? What about you, Rania Frederick? I hope you're there as well, right? You're not just, oh, okay, we have something like, I imagine you mean to the x minus 1. Okay, Christian says something is involved. Interesting, interesting, interesting. I would like to hear from all of you guys. If you can say, well, I cannot solve this problem because, right, I don't know how to solve it, or give me something there, okay? Because I need to, you see, if you don't have any reaction, I do not know what you're thinking about. Dana Phillips, I'm not sure. Well, let's do it this way, okay? Since you are not sure, you think you, and somebody says, I don't know, that's fine. If you don't know, it's good. You can say you don't know. And if you do, then write something, okay? Not sure, I think it is, okay. Okay, interesting. Not very sure. Okay, guys, so let's do it together. Yes, let's do it together. Are you ready? David Wang, okay, good. Okay, so it's very simple, guys. Yes, it's very simple. Afterwards, we all love shortcuts, correct? So what's the derivative? Let me write it over here. So all it is just I take the x and I move it in front. That's the power rule, yes? So I have x, 2, and then I subtract 1 from the power. Some people suggested it, yes? X times 2 to the power of x minus 1, right? Isn't it simple, guys, right? We have this power rule and we can do it. So write to me, please, understood if you got it, how I did it. I want to see lots of understanding from you. Understood, oh, beautiful. Yes, great. What about the rest of you? Do you understand? Got it. What about the rest of you? Come on, guys. Yes, we understand. We are understanding. Yes, sir. What about the more of you? I want to see more understanding. So I know who exactly here in this class understands. Yes? Any more that understand? Because what you understood is wrong. It is incorrect. Don't use shortcuts when you don't understand what you're doing there, right? Of course, maybe it's nice. Some people said they don't know, and that's good not to know, right? Or think about it. Let me erase it and now go through the explanation. you know, I once will get tired of the entire thing. I'll teach the class incorrectly. I will just shove propaganda material in your brain, and you will just come up knowing not know what, right? I lied to you, and it's good, Christian and others that were not sure. I'm pretty proud of you, right? I'm glad that you see, don't buy into what other people tell you. Even if I say that, doesn't mean it's true. It usually does, but not when I don't want it to be true, right? So here, this is wrong. And here is what you were confusing if you used this, what do you call it, power rule, right? Here is the polynomial phase. It's x squared and 2x. You understand? We have x squared, which follows because it's a polynomial and follows the power rule. And let's say this is the phase that you see. And what is 2x? It's this. The mouth is above the eyes. You understand? This is what you're confusing. It's a very, very different creature. Do you understand? 2 to the x and x squared are entirely different creatures. Here, the power is fixed, base is changing. Here, the base is fixed, power is changing. That's why it's called exponential function. And maybe I shouldn't put this exponential function as a title. Maybe I will confuse more of you, right? And when you confuse one with the other, I have a feeling you are this. That's the feeling I get when I hear that thing confused, right? So let's quickly review what are exponential functions. So first of all, if it's an integer, we are just using bookkeeping, right? A cubed, it's a times a times a. And a to the power of n, it's a times a times a n times. Good? Now, we can go. I hope you understand, guys. Exponents. Then we have a. What is a cubed times a squared? That's just simply a multiplied by itself 3 times, then again multiplied by a twice, and altogether a is multiplied by itself 3 plus 2 times. That's why we have the addition property, right? Subtraction happens because we can divide. You understand how subtraction works? Maybe I will quickly mention that in case you don't remember. So what is, for example, if I have a cubed divided by a squared, what do I get? I get a to the power of 3 minus 1, right? And if I want this rule to hold all the time, minus 2, I'm sorry, not minus 1. If I want this rule to hold all the time, I am going to define a to the power of minus n, where n is a positive integer, to be 1 over a to the n. In other words, the minus in the numerator means that once cancellation has taken place, only the denominator survived. You understand? So for example, just to make it clear, I hope it does. For example, if I have a to the power of 5 divided by a to the power of 6, what I will be having is a to the power of 5 minus 6, which is a to the power of minus 1, yes? If I have this notation. But for this to have any meaning, a to the power of minus 1 has to equal 1 over a. This is just saying that denominator a survived, numerator a's did not survive. Good? That's how this works. So now can anybody tell me what's a to the power of 0 and why? If you understood my explanation, what's a to the power of 0 and why it is equal to that value? A to the 0 is what? Why is it 1? But why is anything to the power of 0 1? What if I said anything to the power of 0 is 7? Why am I wrong? You see, when you say any number to the power of 0 equals to 1, well, is that true? What about 0 to the power of 0? Is this defined? What is a to the power of 0, guys? So what if I were to write, let's say, this as a to the power of 1 minus 1? That might mean a divided by a. Do you see it now? Why it's 1? You understand what subtraction means? Subtraction means you have a bunch of a's in the denominator, right? That's the idea of this notation. You're just creating algebra in the power of a. Do you see why? So a to the power, let's first observe. If a is not equal to 0, then a to the 0 is... a to the 0 can be thought of as a to the power of 1 minus 1. But that means the same as there is 1 minus 1 means 1a in the numerator, 1a in the denominator. You understand? So if I write this, it's like there is a battle between the a's, and I have a number divided by itself, it's 1. That's why a to the power of 0 is 1. If you understand this explanation, tell me what's a to the power of 0. So what's 0 to the power of 0? Apologies. 0 to the power of 0 is what? Exactly, undefined. Denominator is 0. 0 to the power of 0, well, you cannot divide by 0 in the denominator, it's undefined. Make sense? All right, let's move on. So you have this basic idea about exponents. With some amount of work, you will observe that in general, it will be quite a lot of amount of work, but you have to understand what roots are and all sorts of things that you can justify in so many ways. But a to the power of x times a to the power of y will be a to the power of x plus y, regardless of what x or y are. Okay, so now let's try to differentiate a to the power of x for any base. So this was the problem of differentiating 2 to the x, but now let's try to do it for an arbitrary base. You understand? And this is the first time where the definition that I will prefer for the derivative is this notation 2 definition, right? It's with x plus h minus f of x over h. That's preferable for this function. For all the functions we considered up to this point, it's much better to use notation 1. Okay? But notation 2 is much better for this problem. So what happens? Well, we have limit as h goes to 0, f of x plus h minus f of x over h. That's a to the power of x plus h minus a to the power of x divided by h. Good? Are you with me, guys? And why did I prefer this notation is because I can factor it out. What is a to the x plus h is, according to this property, it's a to the x, a to the h. Yes? And now I can factor out a to the x out. And this is what I get. A to the x can be factored out, and I have a to the x limit as h goes to 0, a to the h minus 1 over h. Which, let me show you what it is. If I write it in another form, it's limit as h goes to 0, a to the power of 0 plus h minus a to the 0 over h. Are you with me? Now, let me ask you, and this is where I need your recognition and your understanding of what just happened here. This here, don't look at f, x, etc. This means that I took the derivative, I was taking the derivative by the definition at an arbitrary point x, right? To calculate the derivative, I have to zoom in, and I zoom in at some arbitrary point x, and I want to see if it's a line. Now, having to zoom in at some arbitrary point x, what is this red circle here? What does it mean? It is what? I don't mean solve it, guys. You understand? Solving is another thing. I mean name it. What is this thing describing? If this here describes the derivative at some arbitrary point x, then what is this describing? You understand, guys, what I'm asking, right? So you are used because of school or other reasons. You're used to think. Well, I ask you, what's the answer? Oh, it's 5. It's 7. No, that's not how you think. What is the description? What is it about? Here, here's how I understand it, right? It's a sentence. It's an entire journey. Here, a spacecraft or a bug or whatever it is, it's landing on some strange curve, and that curve is basically the coordinates where we are landing is at some point x, and we are trying to understand if it looks like a straight line locally, and what's the slope of that straight line. That's what this is representing. Yes, derivative, I'm just calculating the slope of that straight line where I'm zooming in. So I imagine, that's what I imagine a spacecraft flying into some strange convoluted structure in space that happens to be a curve, and as I'm landing on that, maybe it's like, since it was scanned, I think that's a piece of my hair or something, right? You can see it here, right? So I'm landing somewhere on this curve, and locally it looks like a straight line, and I'm measuring its slope. So then when I'm landing at x, suddenly I realize that my calculations are happening somewhere else. What is this here? You understand? I shift my description. This is slope at point x, and what is this? At 0, exactly. Do you understand what happened here? It doesn't happen usually, right? You zoom in the point x and you calculate the slope there. Suddenly you realize that that you need to calculate not at an arbitrary x, but at 0 specifically. With the exponential functions, you don't calculate it at x, but you calculate it at 0 specifically. So all the slopes that you ever try to calculate, you actually only end up calculating at 0. Isn't it interesting, right? So what is it? Does it look like? You understand? I did not answer what the limit is, as you think, oh, it's 5 or 7. I used recognition of what happened here. I was zooming in at the point x, and suddenly I realized that all I care about is the point 0. I need the slope only at 0. And if I have that, if I know this limit, I know the slopes everywhere. 0 is the deciding slope. You follow? So this is not a simple derivative, guys. It's not something that you can algebraically, like we did before, clear away. That's already the first example of limits that are not trivial at all. You will not, unless you're very clever, you will not right away figure out what's the limit. You cannot just factor it out, eliminate the h so simply. But here is what we are able to figure so far. So the derivative of a to the x exists if and only if the function is differentiable at x equal to 0. So, and the derivative has this form. It's the function multiplied by this derivative at 0, which I don't know. I just denoted as f prime of 0. I presume that it exists. You understand? So the derivative is going to be my original function multiplied by a constant number, which I do not know. I just call it f prime of 0. You follow? I'm reasoning in now quite different. I'm using a different strategy to figure that out. I cannot solve this limit, so I pretend that I did solve it, and I give it a label. I call it f prime of 0 because it looks like the derivative at 0. And if I give it a label, I pretend I have this number. So the derivative of a to the x is a to the x times that number. You follow? In other words, the derivative of a to the x is essentially the same as a to the x. It's not very different. And here is what happens if I take more than one derivative. So take the derivative once, it's the constant, it's just a number times the function. Take the derivative again, we know derivative of a function times a constant is, I can just skip the constant. So it will be the constant squared times the number. And take the derivative again, it's the constant cubed times a to the x. You understand? So what happens when I take more derivatives is just I take this number to higher powers. Are you with me? Right, yes or no, or do you need more explanation, guys? Do you understand what it's not like I did before? I'm actually being much more abstract here. You pretend that you solve this problem. You know, so the problem was so hard that you pretend that you solve it, and that's very powerful. If you remember, it's actually already an ancient belief. It's very common. You know that many people believe that when you give something a name, then you understood it. You have power over it. Right? So how was Adam the master of the animal kingdom? Is that the animals were paraded before Adam and he named them. And this has an interesting truth. You see what's the truth is that I am able to go forward. You see, you could say, well, I don't know what this limit and not move forward. But what you can do is bypass the difficulty of actually calculating it and pretend that you calculate it. You do that actually all the time. You think it's cheating, but you do this cheating all the time. Do you know what is root of 25? Root of 25, you can say it's 5. Correct? But before you say it's 5, the more interesting question is, what is it that you are asking? You are asking for a positive number that when multiplied by itself gives you 25. Does it make sense? So you can guess that this is guessing. You can guess it's 5 when I give you 25, but what would it be if I ask you for this value, root of 5? Root of 5, it means just find me a number that when multiplied by itself gives you 5. And instead of finding it, you keep this as your label. You pretend this is the solution. So when you solve the equation, for example, x squared minus 5 equal to 0, and in school they told you, oh, you solved it very well. Your answer is x equal to root of 5 or x equal to minus root of 5. Yeah, and you get full credit in your school. You know what you did truly? You said, oh, the solution is whatever solves this equation. That's what you said, what you truly did. And you said, oh, it's the positive thing that solves this equation and minus of that positive thing that solves this equation. But you haven't answered it. You understand it? You haven't answered it in a way that you think usually what an answer is. You're just used to this thing and you haven't wondered. What is root of 5? It's the same thing as I did with f prime of 0. It's giving a label. It's claiming that an answer will exist. It's just that you do not know what it is. Are you with me? And that's very powerful because once you can give it a label, you can then eventually figure out techniques to actually carry out an approximation or carry out the actual calculation. Good, but it's just you're playing with labels, and you do that all the time. It's not the first time you see that. It's just you haven't observed root in that perspective most likely, right? You imagine that you solve this question. You understood what I said about the x squared minus 5, guys, right? Again, that when you give the solution x equal to root of 5 or minus root of 5, you're just saying whatever solves this equation is what solves this equation. And you just give it a name so it looks like you gave a solution. But you did exactly the same thing as we do here. So I cannot solve. I just look at it, I carry out this definition, and I cannot solve this limit. But I recognize that it's of the form derivative at 0, of the same function at 0. So I call it f prime of 0, and that's just giving it a label. It's like root of 5. Giving it a label, that I hope the solution will exist. And if it exists, I see what derivative would look like. It's the number multiplied by the function. And if I take more derivatives, it's the same number going to be multiplied by higher powers. Good? Now, because it will bother you, perhaps, we can try to estimate this value using a calculator a little bit, right? So if you are not able to take the limit is just a fancy way of saying h is very close to 0, right? So I need to know what's 2, let's say for the derivative when a is equal to 2, what it's 2h minus 2 to the 0, which is 1, divided by h, right? 2 to the h minus 1 over h. Limit as h goes to 0 is the derivative of 2 to the x, where x equal to 0. You agree? This is just 2 to the 0 here. And if I cannot calculate this limit, I can instead plug very small values of h, you see? So it will be roughly the same as if h is really, really small, right? Limit is perfection, but if I cannot achieve perfection, I can just select h to be very small. Now let me select h to be 1 out of 1,000. It's just an arbitrary choice. Yes, I selected it, and when I carry out in the calculator, I press it in the calculator, I get that this number is roughly 0.69. So for 2, it's 0.69. Now you understand? So then that means that the derivative of 2 to the x is essentially, it's like roughly 0.69 times 2 to the x. And if I take the nth derivative, you see that means take the nth derivative, put in parentheses. That means take one derivative, another, it will be 0.69 to the power of n times 2 to the x. And if you do that, let's say with the number 3, you do it with the number 3, that will be 3 to the h minus 1 over h. I can arbitrarily, I decide that 1 out of 1,000, 0.001 is kind of close enough to 0. I hope. I mean, there is no reason for it really, that only that I think it's pretty small, so I hope it's gonna work. And I use this to calculate using my calculator, and I get 1.099. So that means that the derivative of 3 to the x is roughly 1.099 times 3 to the x. With me? So here is a comprehension check, guys, right? I want you to give me an estimation using your calculators, if you would prefer, what's the derivative of 2.8 to the power of x? If you understand what I mean, right? So you have a calculator or your smartphone or whatnot. So I want you to write out the definition of the derivative for 2.8 to the x, and then estimate what it's roughly like. Say hello to one of my little kitties. Very nice. Okay, somebody did it already. Yeah, 2.8. Good. Okay, guys. So let's see it. Here is all we need. We need the derivative at 0. We cannot calculate the derivative at 0. Let's just plug, again, this is arbitrary number, right? I plug something that looks small, close to 0, and I have an estimate of what the derivative might be like. Make sense? And it's roughly 1.03. Yes. You understood how we did it? So the derivative of 2.8 to the power of x is essentially, well, it's roughly 1.03 times 2.8 to the power of x. And here is a remark that I want you to carry to heart, right? We have cheated a little or maybe a lot when we're using a calculator. The reason for that is, how is the calculator able to carry out this calculation? It might be a tedious calculation that you don't want to do, that's okay, but do you know how the operation is happening? So if I take 2 to the power of 1 over 1,000, it's like you're taking 1,000th root of 2. I bet you don't know how to calculate just the square root of 2. If I left you without any devices, would you figure out how to estimate what's the square root of 2? Or of any other number of the sort, right? So, so this is only for you to feel that there will be a number, but it's not really, it should not convince you at all. Good? Should not convince you. But here is the last question, guys. Before we go, one last question. So if I take the derivative of a to the x, it appears that I will get a constant that depends on a, right? We saw that it's a different constant for 3 and for 2, right? It's a different constant. The question is, when I take the derivative of a to the x, what do you think is the best constant possible that you might ever get? Write it in the comment, and then we'll call it a day. What's the best possible constant? You see, we played around with 2 to the x, it was roughly 0.69. With 3, it was over 1. With 2.8, it was slightly over 1. What's the best constant that we can hope for? Christian, you're absolutely right. The best constant we can hope for is 1. And that it gives us, we cannot hope for 0 because the function isn't constant. It's not a horizontal line, right? It's obviously not, because any a to different powers, it's going to be a different thing, right? And yes, so then we are hoping we can find a number which we call e, whose derivative is going to be 1 times e to the x, which will be e to the x. It will be a function unaffected by the derivatives. And that just naturally implies that the limit as h goes to 0 of e to the h minus 1 over h is 1. In other words, I'm hoping to find a number for which this limit is known to me. It's 1. I engineer the number so it will be 1. Instead of solving the limit, I want it to be solved into 1. I want the problem to modify itself and solve to 1. You understand? That's really what I will think about. Instead of solving the limit, I actually find a solution, and I want a question that whose solution is 1. Are you clear how we're changing our perspective? And the next chapter, it's f of x is equal to e to the x, is something that we will study in great detail. And one of it, if you're interested, it has to do with your birthdays. So for next lecture, I would like to know your birthday, all of your birthdays, and your social security. Take care. Good night, guys. Or if you want, stay for office hours.